Hello everyone, and welcome back to Nuclear Reactor Kinetics and Dynamics lectures. Today we'll continue discussing methods for quantifying the stability of control system transfer functions. The method on today's menu is the Root Locus method. Recalling the standard form for control systems transfer function, we are frequently interested in understanding how the gain, or static loop sensitivity, of control elements affect a system's stability. The gain generally appears as a constant multiplier in the feed-forward element g, where g equals the gain, k, times some numerator s polynomial divided by some denominator s polynomial. The gain of a system could represent the amplification in a proportional or integral or differential control element, but it could also equal the initial power of a nuclear reactor. As we've mentioned before, and will mention later, the power of a reactor can have a significant impact on the reactor's stability. For example, reactors are often unstable at lower powers because the system's power is just too low to generate any feedback. Recall the characteristic equation of a control system's transfer function, where the roots of this characteristic equation dictate the system's stability. Again, any roots in the positive real half-plane mean that the system's output will contain an increasing exponential term and will thus be unstable. G of s and h of s are often fractions as a function of s, and gh can be represented by some gain k times the product of s minus some z1, s minus some z2, s minus some z3, etc., all divided by the product of s minus some p1 times s minus some p2, s minus some p3, etc. The z terms in this expression are known as the zeros of the numerator, while the p terms are known as the poles of the denominator. When we simplify our characteristic equation so that it contains no double fraction terms, it becomes equal to the denominators of g and h plus k times the numerators of g and h, written again here using the pole and zero terms. As the gain k approaches 0, our characteristic equation becomes equal to just the denominator terms, which means that the poles dictate the roots of the characteristic equation. Likewise, as k approaches infinity, the zeros of gh will dictate the roots of our characteristic equation. So you can see that the gain impacts which terms dictate the roots of our characteristic equation. As the gain of our system increases, the roots too will change. Root locus plots are a way of plotting this gradual shift from pole-dominated roots to zero-dominated roots. They are a great way for determining for what gains our system is stable or unstable. To create a root locus plot, we must first count the number of poles, n, in a characteristic equation, and also the number of zeros, m. Like an overly complicated game of tic-tac-toe, root locus plots denote the poles using an x and the zeros using an o. Generally, but not always, our plot will feature more poles than zeros. So from here, how do we generate a root locus plot? Just as when evaluating Roth criteria, making a root locus plot like this one here, for example, our options are to either use a code to generate the plot or to try generating it by hand. Again, the root locus plot uses these arrows here, which are known as the loci, to show how our characteristic equation's roots shift from the poles, the x's, to the zeros, the o's. But how do we know where each locus starts and ends, and how can we predict when loci will exhibit this asymptotic behavior here? There are quite a few rules to follow when generating root locus plots, but we will review the most common rules to follow. First, the number of loci, which are the arrows in our plot, is equal to n, which is also the number of poles in our characteristic equation. Because n is usually greater than m, this number is generally equal to the highest order of the s polynomials in our characteristic equation. Next, we note that all loci originate at the poles and then that they will terminate at the zeros. So they go from the x's to the o's. When traveling towards the zeros, the loci cannot intersect. If n is greater than m, then we don't have enough zeros for all of our loci to travel to, which means that n minus m of our loci will approach infinity along asymptotic lines. The angle at which these loci approach infinity is equal to 180 degrees plus or minus some constant k times 360 degrees, all divided by n minus m, where k is equal to 0, 1, 2, all the way up to n minus m minus 1. The centroid around which these asymptotes are centered, which is sigma c, is equal to the sum of the poles minus the sum of the zeros, all divided by n minus m. Lastly, whenever loci leave the real axis, also known as breaking out, to avoid intersecting, or enter the real axis, which is known as breaking in, they must do so at a 90-degree angle to the real axis. These rules seem kind of arbitrary and difficult to understand, so let's exercise them by making some sample root locus plots. First, we'll do an example where GH is equal to some gain k times s minus 2 divided by s plus 1. In this case, n equals 1 and m equals 1, which means that we have one pole at negative 1 and one 0 at positive 2. We plot our 1x and 1o in the complex plane, and because we have one pole, we must have one locus, which travels from the pole to the 0, like this arrow here. Well, that's it for this first example, and for our next example, our GH function is equal to k divided by s times s plus 3. This means that we have two poles, one at s equals 0 and one at s equals negative 3, and that we have no zeros. Because n minus m equals 2, this means that we must have two asymptotes. We next use the theta equation to find the angle for our two asymptotes. Since n minus m minus 1 equals 1, this means that we need to evaluate our thetas at k equals 0 and k equals 1, which then becomes equal to 90 degrees and 270 degrees, which is just also equal to negative 90 degrees. The centroid around which these asymptotes are located, sigma c, is equal to the sum of the poles minus the sum of the zeros divided by n minus m, which equals negative 1.5. Because these asymptotes break out into a plus or minus 90 degree angle, this means that the asymptotes' centroid is also equal to their breakout location, which we will discuss more in a second. So from here we draw the two loci starting at the poles, which head towards each other until they reach the breakout location, s equals negative 1.5, at which point they break out to angles of plus or minus 90 degrees. Note that the two loci don't actually intersect at the breakout point. They veer away from each other at the very last second towards their asymptotic paths. Our last root locus example has a GH function that's equal to k times s plus 3 divided by s times s plus 1 times s plus 2 times s plus 4. This means that we have four poles at 0, negative 1, negative 2, and negative 4, and 1, 0 at negative 3. Because n minus m equals 3, this means that we must have three asymptotes. We can evaluate the angles for our asymptotes using little k is equal to 0, 1, and 2, which means that our thetas take place at 60 degrees, 180 degrees, and negative 60 degrees. The centroid around which these asymptotes are centered is equal to the sum of the poles minus the sum of the zeros divided by n minus m, which equals negative 4/3. Drawing these asymptotes is not quite as straightforward as it was in the previous case. Because we have an asymptote that heads off at 180 degrees, and we know that loci can't intersect, this means that this locus must start at negative 4 and must go towards negative infinity. Next, we know that we must have a locus that terminates at s equals negative 3, and because loci can't intersect, we know that our next locus must originate at s equals negative 2 and terminate at s equals negative 3. Logic stands to reason that our two remaining asymptotes start at these other 2 points, but what is the breakout point for these asymptotes? It certainly seems like this breakout point should be between the loci at s equals 0 and s equals negative 1, since the loci can't intersect, but let's find out for sure. Because we know that the angle of the loci at the breakout point must equal 90 degrees, this means that the derivative of k of s with respect to s must equal 0 at the breakout point sigma. Given that our characteristic equation must equal 0, this means that our gain must equal negative 1 divided by gh. Solving for dk ds equals 0 gives us that sigma must equal negative 0.43492, which, as we expected, is between the s equals 0 and s equals negative 1 poles. Lastly, we'll solve for the value of the gain at the breakout point, which we find is equal to 0.53459. Armed with this information, We can finish drawing our root locus plot. We finished our last example by computing the gain at the breakout point, but why does this breakout gain matter? Well, at the breakout point, our system's roots break away from the real axis into the land of imaginary components. Recalling that imaginary roots imply that our transfer function has sinusoidal behavior, we see that this breakout point corresponds to the location where our transfer function gains oscillatory behavior. For reactors, oscillatory behavior can be very undesirable. A reactor transient that ends with a stable power is all well and good, but a reactor that oscillates up to 500% of full power on its way towards stability is almost guaranteed to melt fuel. So depending on the reactor and the situation, we may sometimes wish to ensure that transients do not have oscillatory behavior, and solving for the gain at the breakout point is one way of doing this. We'll finish today's lecture by solving for the gain where the characteristic equation's roots cross the imaginary axis. Since positive roots mean that our system will become unstable, solving for the imaginary axis crossing point gives us the gain that will cause our system to become unstable. When our roots cross the imaginary axis, we know that the real component of S must equal 0, and we'll assume that our imaginary component of S is equal to I times some omega. So since we know the general form of S, we can substitute it into our characteristic equation, which equals 0 again, and then solve for the values of omega and k. For a previous example, simplifying out our fractions gives us this expression for the characteristic equation, and we then substitute in S equals I times omega. We can simplify this expression and separate out the real and imaginary terms, which must both equal 0. We can then solve these two simultaneous equations for omega and k, which in this case, we find that omega equals 1.59 and k equals 9.65. Looking back, our root locus plot has told us a lot about our system. We know at what gains the system is stable, and at what gains it develops oscillatory behavior, both of which can aid in setting the bounds for what reactor power will ensure reactor stability. This concludes our lecture on the root locus method. In the next lecture, we'll discuss the last of our 3 stability metrics, and then we'll move on to developing the transfer function for modeling reactor behavior.